Chapter 8 is about the quantum mechanical model of the atom. And it starts off with this great quote from Niels Bohr: "Anyone who is not shocked by quantum mechanics has not understood it." So I'll just warn you ahead of time. We're going to talk about some stuff that is not going to make sense and it just seems to defy reason, and you're not going to like it, and nobody really likes it, but it is what it is, and you have to learn about it anyway. So the beginnings of quantum mechanics. Up until the beginning of the 20th century, everyone believed in nice classical physics, right? Deterministic. So if you have a ball and it's traveling through the air at this trajectory and this speed, you can predict where it's going to go, right? But work done by many famous physicists discovered that for subatomic particles, that's not true. The present condition does not determine the future condition. So if you shoot an arrow or a baseball with a certain velocity in a certain direction, it's going to hit a certain spot, and if you throw it exactly the same under the same conditions, it's going to hit exactly the same spot every single time, right? That makes sense to us. If you do it with an electron, it's going to land in a different place every time. That's wrong, right? It's wrong, because the very, very small things obey different rules. So the absolutely small or quantum world of the electron behaves differently than the large or macroscopic world that we can see. And it would even include the microscopic world, right? So like viruses and stuff, they obey regular physics rules, but the absolutely small does not. Even more disturbing, when unobserved absolutely small particles like electrons can be in two different states at the same time. Not like Arizona and New Mexico, but two different states. So an unobserved radioactive nucleus could be simultaneously emitting a particle and not emitting a particle. So how small are we talking about? Incredibly small. So electrons, a single speck of dust, like, just a little teeny tiny piece that you can barely see. Single speck of dust has more electrons in it than the number of people who have ever lived on Earth. That's a lot of electrons. So the electrons have to be really, really small. We care about the behavior of the electrons because how the electron behaves affects how the atoms behave, which affects the properties of the entire substance. We can't directly observe electrons, for one thing, because they're too small. Not even a scanning, tunneling microscope can observe an electron. But also because if you observe the electron, you change its behavior. So you might have known somebody in grade school who was like this. You're at a play date, you go over to their house to play, so out on the playground at school, right? And there's this bully, and he beats up on kids, except when the monitor is watching, right? If the yard duty is out there, he's fine. Yard duty turns away and he's beating somebody up, right? So electrons are kind of like that. So even shining light on an electron affects its behavior, which is, it's like, wait a minute, are electrons alive? How do they know that something is observing them? I have no answer for that question. So you may have heard of Schrödinger's cat. So this is a thought experiment, and the point of it is to demonstrate how quantum strangeness does not transfer to the macroscopic world. So I have a couple of videos here, because these are better than what I could explain.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So that's a great website called Minute Physics. They got a lot of good videos. So that's one description of Schrödinger's cat experiment, and here's a different one.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the science. And so, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom is decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, And at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
So another cool series of videos. I don't think that means what you think it means. Okay, so questions? So some people love this kind of stuff. I have a nephew who's working on a PhD in some kind of particle physics at the University of Chicago. He loves this stuff. So his research is on. It's like, well, I appreciate the coolness of it. I have no desire to study it. Right? It's weird. It's disturbing. Okay? So there's the quote from Bohr: anyone who's not shocked by quantum mechanics has not understood it. Schrödinger wrote, I don't like it, and I'm sorry I had ever had anything to do with it. And Einstein attempted unsuccessfully to disprove quantum mechanics until he died. Very smart guys. They didn't like it.
Well, you just trying to prove that there was God.
Well, yeah, one of the things Einstein said was God doesn't play dice with the universe, which is what quantum mechanics seems like. It's just like a crapshoot, basically. So don't even try to understand quantum mechanics. I don't understand quantum mechanics. I don't think there's anyone who can reasonably say they actually understand quantum mechanics. They may understand some things about it. We can learn about it. We have to learn a little bit about it, but it is very, very strange because we don't observe things like this in everyday life. And quantum mechanics, like any other theory or model, cannot be proved correct. We can't prove it correct. We can only not prove it wrong, right? Because we keep learning and developing new technology, and there were theories that were believed, and with the current knowledge at the time, they appear to be true, but then later we find out, no, that actually wasn't quite true. And so it's possible that in the future something will come along and supersede quantum mechanics. But for now, this is the state of the art. This is where it is. So it explains, as much as it explains anything, how electrons exist and behave in atoms. And that helps us to understand and predict the properties of atoms, because those properties are directly related to the behavior of the electrons. So the sorts of things that this helps us understand is, why are some elements metals and some are nonmetals? Why do some elements gain one electron when they form an anion? Why do other atoms gain 2 electrons? Why are some elements very reactive and others are practically inert, don't react with anything? And it also explains other periodic patterns that we see in the properties of elements. So it explains a lot of stuff. So we can't ignore it.